Hello, folks. Oh, you can do better than that. Hello, folks. There we go. Come on, I thought sample spaces would excite you much more than that. Okay, so I'm going to review some of the material we covered in the first lecture just to bring everything together, and the main topics for today will be conditional probability and Bayes' rule. And so we'll get to what is arguably the heart of statistical inference, and that's Bayes' rule. Okay, what did we do last time? Well, last time we talked about sample spaces. We defined the random experiment. We looked at the finest grain, mutually exclusive, collectively exhaustive set of outcomes, and we listed them in different ways. Each of those was a sample point, and the collection of all those possible finest grain outcomes was the sample space. We talked about how to draw some typical sample spaces. And I told you this is actually a craft that's very important in problem solving. You have to start playing around with different diagrammatic ways of representing random experiments and get a feel after some time of which kind of diagram is more suitable for the particular kind of problem or the random experiment that you're dealing with. So, for example, I did the six-sided die, but I'm just going to keep it brief here. Let's say I roll a four-sided die twice. So on the first roll, I mark the horizontal axis with the outcome of the first roll, and the vertical axis with the outcome of the second roll. You can see that you have a total of 16 sample points, and assuming that it's a fair die, all of these 16 sample points are equally likely, so the probability that you will get any particular outcome in one of these cells is 1 over 16. So this is a fair four-sided die. Another way we represented sample spaces was using tree diagrams. So, for example, tree diagrams. I toss a fair coin twice. Actually, it doesn't have to be fair. I toss a coin twice, and I represent the outcomes of the outcome of each toss with an index, and whether it's heads or tails, I represent with H or T. So the result of the first toss is either a head, I represent that with H1, or a tail with T1, and then once I have the outcome of the first flip, I toss the coin again, and I have outcomes H2 and T2. And here I messed up. H2, T2. And my sample space will consist of a bunch of these sample points, 4 of them in particular. So I've got heads on the first flip, tails on the second, tails on the first flip, heads on the second, both tails. There's also the simple listing of the outcomes of my sample space. So in this case, listing. In this case, I would just represent the outcomes as a set. I've got H1, H2, all the way to T1, T2. That's another way I can represent things. And of course, there's also the good old Venn diagram. I represent the overall set as omega. That's my sample space. Within this sample space, I can define events, A and B, and within each, I can define sample points. Okay? All of that should be fairly straightforward. We talked about axioms of probability, which is basically the mathematical structure that any measure of likelihood that we want to assign to our random experiment must meet. There were how many of them? 3. First one was? What was the first axiom? Actually, I don't care which one you call 1, 2, or 3. Just give me one of them. Non-negativity. The probability of any event must be non-negative. In fact, the probability of any sample point must be non-negative. And what's the other one? Normalization, which means what? All the probabilities have to add up to 1. And the third one was what? If I have two events that are what? Mutually exclusive, then probability of their union is what? Louder. Imagine you're part of an orchestra. Equals? Boy, you need a lot of training. P of A plus P of B. Fireflies can synchronize better than you can. Come on, you can do better. Okay. And then we worked with these axioms to derive other somewhat intuitive and at least not surprising properties. We derived the idea that the probability of an event not only must be non-negative, but in fact it must be less than or equal to 1. So probabilities are always numbers between 0 and 1. And we also extended the additivity property, and we said that if A1, A2, A3, and so on are mutually exclusive, then what can you say about the probability of their union? I'm cheating here a little bit because we did it for a finite countable set, but in fact it extends in a non-trivial way to a countably infinite set of points. So what can I say about the probability of their union? If you were to extend this property, what would that be? It's not a trick question. The sum of all the probabilities. I from 1 to infinity. Most of the time we'll be dealing with finite sets, but I gave you an example last time of a coin flip experiment where I keep flipping a coin until I get my first head. That sample space is countably infinite. There's no guarantee that I will have a finite ending point. It can go on indefinitely. The likelihood that it gets longer and longer is smaller and smaller, but theoretically I can flip this coin and grass grows under my feet and still I won't get a head. Okay. We also talked about, so these were the axioms. We also talked about when two sets have a relationship like this, when a set is subsumed in another, then the probability of A ends up being what relative to the probability of B? Less than or equal to. And I think we got to this last part near the end of the lecture, law of total probability. I may have gone over this more quickly than what I would have liked, so let me spend a little bit more time on that. So let's say I have partitioned my sample space into a set of mutually exclusive, collectively exhaustive events. This is called an event space. So just like we defined sample spaces, we can also define event spaces. So in this case, I've got 5 events. So A1 through, if in general I have a collection of n of these, are mutually exclusive. and their union gives me the universal set, my sample space, so they are collectively exhaustive. Notice in this case, I'm not insisting on the finest grain property. So that's what distinguishes an event space from a sample space. A sample space has to be the finest grain resolution of the outcomes of the experiment. You can't get any smaller than that. You can't crack open that final outcome into any smaller segment. But with event spaces, these events are just subsets of my sample space. So this is called an event space. Event space. Now, I liked it more when I had my, let's use blue. Let's say I have an event B. And, sorry, I'm a novice with this. Where are the highlighters? Oh, well, I'll just do this. So, I have an event B. This event B will have overlaps with these partitioning events AI. Okay? And I'm interested in figuring out the probability. How does this work here? How did I? Okay, I like this more. And I'm interested in figuring out the probability of the event B. Probability of B. Now, the law of total probability is essentially a divide and conquer law. I can divide my event B into non-overlapping segments. Does this diagram suggest that non-overlapping segment or segmentation? How would I split this diagram into non-overlapping segments? Is that a highlighter? Talk to your neighbor. How would I split this? I want to write the probability of the event B as a sum of a bunch of probabilities of events that are non-overlapping. How would I do that? Here we go. Where's the yellow? Oops. Okay, I'll take a volunteer. Uh-oh. Where's my pen? Pen. Oh, that's not my favorite pen. Black. Okay, there we go. Anybody? Nobody? You are? Alex. Go for it, Alex. So B intersect A1. That would be right here, the green. This is B intersect A1. Okay? And? So what about B intersect A1? The probability of, B intersect A1. Plus the probability of B intersect A2. Why can I do this? What's special about B intersect A1 and B intersect A2 that allows me to do this? I'm not overcounting. They don't have an overlap. In other words, I have partitioned the event B into a set of non-overlapping intersections. So, in other words, what I'm saying is B is the union of B intersect A1 and B intersect A2 and ... B intersect A N. Huh? I can write B in this way. I take each of those little chunks and say B is the union of those chunks. Those chunks don't have an overlap. So when I do the probability of their union, I'm simply adding their probabilities. Probability of B intersect A N. This is called the law of total probability. Thank you, Alex. Any questions on what we just did? Yeah. Yeah, in this case, n is 5, but in general, I have a partition of my sample space that consists of n events. And so in that case, I will just write it as the intersection of A1 through AN. So in this case, n is 5. Yeah. This is what you're talking about. Yes, this is a union. Thank you. Oh, that was a good catch. So I'm representing B as a union of a bunch of non-overlapping sets, and using the additivity property, I'm simply saying the probability of the event B is the sum of all these probabilities. Okay, this will be used very often in our analysis. All right. Let me ask you one more thing to sort out. Actually, a couple of things more. So then we have uniform probability law. Remember the bin I drew for you, and we had a bunch of, let's see, what is a bunch of, so I had black balls in there, I think I had 5. I had 5 black balls. I had a green ball, and I had that's a highlighter. That's not what I want. How do I get my red one? I don't want to use, let's use click on. Oh, there we go. Thank you. Whew. Red. How many red did I have? I had 2 reds. Okay. So this is my sample space. All the balls are identical in shape and texture, so when I stick my hand in there, I can't tell the difference between one ball and another, and I'm not seeing what the color is. I just stick my hand in there and pull out a ball. So you agree that the outcome of one draw is every ball is equally likely to be drawn. Okay. Now, if I define the event G as the event that I pull a green ball, and R as the event that I pull a red ball, and B as the event that I pull a black or black ball, then how would you figure out the probability of, say, R? What's the likelihood that I'll pull out a red ball? Okay, you don't want to tell me, tell your neighbor, and then tell me. Okay. What's the answer? 2 out of 8. 2 out of 8. What's your name? Avi? Abi. So, what did you do, Abi? How did you come up with 2 and how did you come up with 8? 8 balls. So the size of your sample space is 8. This uniform probability law that we're describing applies to finite sample spaces. So the size of the sample space is 8. And that ended up being in the denominator. And where did you come up with 2 from? There are 2 red balls. The event R consists of 2 sample points. So the event R has size 2. Okay? So the uniform probability law says if you want to figure out, if you're living in a finite sample space and all outcomes are equally likely, the way you figure out the probability of any event is by simply counting the number of sample points that are in that event and divided by the total sample space size. And that's what we did here. And if I wanted to figure out the probability of black, I would simply say, what, Abi? Size of B over size of the sample space. Okay? So that's all there is to it. And the probability of an event, say, B, is the sum of all the probabilities of the sample points that are in B. You take the probability of each sample point that's in B, add them all up. Why can I add them up? Because they're what? The axiom. They're mutually exclusive, all these sample points. So to figure out the probability of an event, I simply add up the probabilities of all the sample points that belong to that event. In this case, it would be the probability of B1, the probability of B2, times the let's stick with the same notation. You can use PR if you want, and P5. And each of these, of course, is 1/8, and I'm adding 5 of them. And that's 5/8. That's the probability that I'll draw a black. So that's the uniform probability law. Okay. I want to do one more thing before I get... Any questions on what we've done? Most of this should be review, except possibly this last part that I didn't explicitly say. Yeah. Yes, that's why we call this law. So the question was, this assumes that every ball is equally likely to be selected. Yeah, that's exactly right, and that's why we call this the uniform probability law. We're living in a sample space where all the sample points are equally likely to occur. Exactly. Things become more subtle when we move to continuous probability, because when I have a continuous, where'd you go? When I have a continuous probability set up, let's say I have a square of size 1 and I throw a dart somewhere in there, what's the likelihood that I will hit exactly a particular point, let's say 0.5, 0.5? Now in my sample space, I have an uncountably infinite set of points, so each point has probability 0. So things get a little hairy when we move to the continuous realm, but we'll get there and cross that bridge soon enough. For now, let's just live in the nice, discrete probability world and see what we can hash out and develop. Okay, so that was that. The other thing I promised you I would do was the probability of the union of two events. So here I have a sample space, omega. I have A, I have an event B, and there is a union, there's an intersection here, and the union of the two is, well, the union of the two is the union of the two, and I want to figure out the probability of the union. How would I go about doing that? Can you use the law of total probability to figure out, to write down at least the preliminary equation? Talk to your neighbors and see if you can write a preliminary equation for the union. What would this region be? What is this region? Can you give it a name or a symbol? B intersects with? B intersects with A complement. We use the symbol B backslash A. It's the portion of B that's not in A. If you like, you can use B minus A, the portion of B that's not in A. I don't care what symbology you use, as long as you make it clear what you mean by what you're writing down. Okay, so can you write down the probability of A union? Write down an equation. You've got A union B that consists of 3 segments, or you can split it in some other way. But I would like to know the probability. The goal is to figure out the probability of A union B. What is that? Oops. I don't want you to go that far. Okay. I'll take another volunteer. Soon this volunteer business is going to be gone. Soon we're going to pick people. Yeah, you are. Adrian. Go for it, Adrian. A and so that would be here, right? A and not B. Is that what you're referring to? That's A and not B. Okay. What about it? Take the probability of this. Okay. Plus the probability of A and B. Plus the probability of B and not A. This all gives me what? Wait, so when I add these up, what do I get? This is the probability of A union B. Because if I add the purple or pink, depending on your eyesight, and the white and the yellow, I get the probability of A union B. So we've split the A union B into three segments by the law, three non-overlapping segments, and by the law of total probability, the sum of those segments, the probability of the sum of those segments is the sum of the individual probabilities. Okay, now what, Adrian? So slow down. So A and not B is what? Can you mix a couple of these and just give me the probability of one of these events? I think we've split it into too many pieces here. What happens if I add these two? That's the probability of A. Okay. And how can I write that? Probability of B minus the probability of A and B. So now when I look at the universe of the event B, that sub-universe, I can split it into two segments, the yellow and the white. And all we're saying is that the sum of the yellow probability and the white probability gives me the probability of B. So that means the yellow probability is the difference between the probability of B and the probability of the intersection. And I have my equation. So on the left-hand side, let's bring this to the left-hand side. So the probability of the union is equal to the probability of A plus the probability of B minus the probability of the intersection. We subtract the intersection probability because by adding the probabilities of the two events, we are double counting the intersection probability. So we have to take it away. Okay? So this is called the inclusion-exclusion. I'm not really big on these names. I care more about you just being able to articulate what these are. Inclusion-exclusion principle. You've already done this when you studied Venn diagrams and set sizes. When you want to figure out the size of the union of two sets, what did you do? You added the size of this first set, the size of the second set, and you said, okay, we're double counting their intersection, so we subtract that once so that the accounting works out. The only difference here is that you are dividing by the probability or the total number of the sample size, sample space size, basically. And that's how you get the probabilities. Otherwise, the principle is pretty much the same as what you studied when you dealt with Venn diagrams back in high school and counted elements in those sets. Okay. We'll get to some ramifications of this inclusion-exclusion principle later. For now, notice that if two sets are mutually exclusive, that third term is what? Special case is when A and B are mutually exclusive. Then what can you say about the probability of A intersect B? It's 0, which means you are back to the additivity axiom. Right? So the additivity axiom is simply a special case of this. We've generalized the additivity axiom here. That's all we've done. Any questions? I'm about to start conditional probability. Do you need a break? Yeah, question. So, okay, very good question. Why don't we have an axiom that says the probability of the empty set is 0? Because you can derive it from the other axioms. I'll let you think about that a bit. You can derive the fact that the probability, so here's the question. How do we know the probability of the empty set is 0? How? It's a good question. Yeah. Well, the empty set is this oddity in set theory, right? It's always a subset of every set. Yeah. Uh-huh. Let's pick a particular A about which we have an axiom. The sample space intersect phi is what? Is what? Empty set. So the probability of this is the probability of the empty set. Is that what? Wait. Let me see if that's going to get me where I want. No. That's not what I want. I want this. What's the union of omega and phi? Omega. And what can I say about the probability of the union of omega and phi? Let's not split that. On the right-hand side, you have what? P of omega, which is what? 1. How do I massage this? Now I come back to you. I'm going to have you answer your own question. How do I massage the left-hand side to get the result I want? Can I break this up? Why can I write the left-hand side as the probability of the sample space plus the probability of the empty set? Because their intersection is the empty set. Therefore, by the additivity property, this equals P of omega plus P of phi. And this is equal to what? P of omega, which is what? 1 plus P of phi. And on the right-hand side, I have 1. So what does that say about P of phi? 0. I don't need a new axiom. The whole point of having axioms is that you have distilled everything else everything you need to know into as few assumptions as possible. Axioms are assumptions at the end of the day, right? So I want as few assumptions as possible. And from those that smallest set of assumptions, I want to be able to derive the whole universe. That's the idea. So I don't add P of phi equals 0 as an axiom. You can rearrange axioms, so you might come up with a different set of axioms. As long as it's a minimal set and you can derive everything else from it, you have a valid set of axioms. Okay? All right. Let's take a two-minute break, and then we'll start conditional probability. Okay. I've got a couple of dice, and I can assure you these are not trick dice. Each has 6 sides, properly labeled. I've got an orange die and a green die. And I roll these dice, okay? So, what's my sample space size? If this is, I'm not going to bother trying to figure out how to get orange here, so let's say red approximates orange die. And I have a green die. So how many sample points do I have? Everybody. That is not everybody. Oh. No wonder you should, there's nothing for you to see. What's the sample size? The dice are sitting in front of you. What's the... Thank you. Oh. Okay. So I've got 6 for each. 3, 4. Is that right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Okay. So we've got 36 outcomes, and I tell you that the sum of the 2 readings is 4. Okay? So, the event, I define an event B, which is that the sum is 4. Can you draw or highlight? Help me highlight those points corresponding to event B. 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. What should I highlight? 1 and 3. Okay. 3 and 1. And 2 and 2. Okay? So yellow is my event B. Now, I ask you, so this consists of the points 1, 3, 3, 1, and 2, 2. And I ask you about the probability that the green is a 1. Let's call that event A. Before I gave you this information, how would you have drawn A? How would you highlight A? Which row? Oh, first row. This is A, right? And so it's basically 1, 1, 2, 1, all the way to 6, 1. So the probability of A is what? Everybody, how do I figure it out? What law do I use? The uniform probability law. Uniform probability law says what? The numerator takes what value? I will be as uncooperative with you come midterm time as you are with me right now. What goes around comes around. Help me out here. What is the numerator? 6, which is the size of A over size of omega. Size of A is 6, omega is 36, so it's 1/6. But now I've given you partial information about the outcome. I've told you that the sum of the 2 rolls is 4. Given that the sum of the two rolls is 4, whoops. Whoop. No, that's not what I wanted. Given that the sum of the two rolls is 4, can you reassess the likelihood that the green die ended up with a 1? This is how we denote it. Given the event B, what is the probability of event A? The moment I give you this partial information, your universe of possibilities changes. You have a new sample space. We call it a conditional sample space. All the laws and axioms of sample spaces apply here. The only thing you have to do is renormalize everything so everything adds up to 1. Okay? So, given that the sum of the two rolls is 4, what is the probability of the green die showing a 1? Can you identify that on the chart? So, walk us through. First, tell me which cell I should highlight further. Green is 1 and orange is 3. This cell right here. Correct? Once I tell you that the sum of the two dice is 4, I'm restricting your possibilities. And the only way that the green die can be 1, given that the sum is 4, is if this had been the outcome, right here. Symbolically, what does this represent? What is that cell? When you look at the blue highlight and the yellow highlight, what does that green squiggly cell represent? The intersection of the two. Okay? And what is the probability of that cell in the original sample space? No, in the original sample space. 1/36. I have to renormalize everything. What is my new sample space, the conditional sample space? What universe am I living in right now? What? Which is what? What color? Yellow. My new sample space, my conditional sample space is the yellow region. I've told you B has happened. I'm in one of those 3 yellow cells. Right? Now that I'm in one of those 3 yellow cells, I'm asking you what's the probability that I'm in this cell that I've squiggled with green. The final answer should be? What do you think the final answer is? We're restricted to one of these cells. I'm asking you what the probability is of this cell having occurred, given that I'm in one of these 3. 1/3. My final answer had better be 1/3. So what goes in the denominator to make that happen? 3/36. What is 3/36 when you look at this diagram? Probability of B. Beautiful. So I gave you partial information about the outcome of the experiment. It constrained the possibilities that you could fathom. Within that conditional universe, my conditional sample space is the set of these 3 yellow boxes. I no longer live in a 6x6 grid. I live in a 3-box grid. Okay? Now that I'm living in that set of 3 boxes somewhere, what's the probability that I am in this particular box? Well, they were all uniformly likely, equally likely to begin with. In the new conditional universe, they are going to remain equally likely. In other words, the proportionality is preserved. If two outcomes are equally likely in the original universe, when I condition the sample space, they remain equal. If they had a particular ratio, if one was twice as likely as the other in the original space, in the new universe, they will still retain that 2-to-1 ratio of likelihoods. All we've done is renormalized our probabilities. And the normalization factor is what you see in the denominator here. Probability of B. The conditioning event. So, let me just write that again. Probability of A given B is the probability of the intersection over the probability of B. This is the normalization constant. And this is read the probability of A given B happening, or given that B has happened. This is called conditional probability. I can change the question. So, did I give you useful information? Let me ask you that. Did I give you useful information? What was your unconditional probability of A? What was the probability of A? Before I gave you that piece of information about the sum being 4. 1/6. But now I tell you that the sum is 4. And it altered your assessment of the likelihood of A. Okay? This is characteristic of events that we call dependent. The event A depends on event B. I will talk about independence in the next lecture. I don't have enough time today to go over it. I want to get to Bayes' rule. But, yeah. Yeah, so there's a generalization of this to multiple events. We'll get to that. Yeah, the expressions become a little more complicated. Let's cross this bridge first, make sure we're all on board. But that's an excellent question. What happens if I condition it on 2 events? Yeah, all kinds of permutations can happen. 2 events that are dependent unconditionally become independent conditionally, or vice versa. All kinds of cool things can happen. Now let me ask you another question about the same experiment. Now I tell you that the sum of the red and blue so let me redraw. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now I tell you that the sum of the 2 rows is 7. So let's say event C. Sum of 2 rolls. Same dice. Sum of 2 rolls is 7. And A is the same. A is, so this was what? Green. And this was orange. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And I say green is 1. Can you identify event C for me on the diagram? Where would it be? What's your name? Pardon me? Omotara? Cool name. Awesome. Talk to me, Omotara. How do I shade this? Did you give me the diagonal or the counter diagonal? Is it this one or this one? Yeah, I ask all the questions around here. I'm just kidding. This one? Well, test one of them. Is this one? Yeah, okay. So this is my event C. What's the probability of C? Huh? No. You're on the hook, Matara. 1/6. How'd you get that? 6 over 36. That's 1/6. Okay. Now the probability that that the green roll is a 1, given that the sum was 7. Which box should I shade? Bottommost right one. This one right here. So what's that conditional probability? In my new universe has how many sample points? Well, you're one step ahead of me. My new universe, event C, has how many sample points? 6, right? And out of those 6, only one of them corresponds to the event I'm interested in, 1/6. Again, this is the probability of A and C divided by the probability of C. Did I give you useful information, Omutar? I did? Well, let's figure it out. Before I told you that the sum was 7, if I had asked you what's the probability that the green roll will be 1, what would you have told me? 1/6. Yeah. Exactly. So, this is an example of two events that are independent. In other words, your assessment of the likelihood of the probability of A before I gave you the information did not change after I gave you the information. So, in this case, the probability of A given C happens to be the same as the probability of A. It's as if I may as well not have wasted my time and made you do all this work. I didn't give you anything useful. Huh? This is an example of, so we say that A and C are independent. I'll get to this dependence and independence in the next lecture, as I said. In the first instance, your assessment changed. In the second instance, your assessment did not change. Okay? All right. Now, what is this Bayes rule all about? Let's go to Bayes rule. I have a pet peeve I have to tell you about. I insist on the apostrophe S. Maybe after 10 years of therapy, I don't worry about the apostrophe S, but right now I do. So, what is Bayes' rule? We've said that the conditional probability of A given B is the same as the conditional probability of the intersection over the probability of B. Right? Which means that the probability of A and B is the same as the probability of A given B times the probability of B. Correct? Can I not reverse the roles of A and B here? What if I asked you, what's the probability of B given A? What is the definition of conditional? By the way, before I forget, conditional probability is only defined when your conditioning event has non-zero probability. Otherwise, it's undefined. So when I say probability of A given B, this denominator had better not be 0. Huh? Otherwise, we're talking nonsense. So this is only valid when P of B is a positive quantity. So now, what is the probability of B given A? What does the definition tell you? What's the numerator? intersection of A and B. Great. And what's the denominator? Probability of the conditioning event. Which means that the probability of A intersect B can also be written as the product of these two here, right? I can write that as probability of B given A times the probability of A. What can you tell me about the right-hand sides here? They're equal. They must be, because they both correspond to the probability of the intersection. Okay. Well, if I make them equal, then it means that probability of A given B times the probability of B, right here, okay, is equal to the probability of B given A times the probability of A. And now I have a relationship that is astoundingly beautiful, very controversial, and not following which has caused tremendous disaster in all realms of life. In medicine, in law, in politics. This is called Bayes' rule. Thomas Bayes was actually a theologian. It was a reverend. It was a priest in England. He had no desire to have any kind of fame whatsoever. In those days, it was the question of what we can infer about partial information about life was very important. What he did was actually he scribbled these things down and gave a note to one of his friends who was also a priest and a mathematician who presented this after his death. And the rule was named after him. Think about the following scenario. Actually, let me draw that out. It's better. So, basically, Bayes' rule allows you to reverse the order of the conditional probability. The likelihood that A has happened given that B has happened can be expressed using this formula in terms of the probability that B has happened given that A has happened. So, to make that a little more concrete, let's look at an example. Let's talk about HIV testing. I have a population of people. Let me make sure I get my numbers here so I don't confuse myself. If I take a person at random from my population, the likelihood that that person is HIV positive is 5%. Okay? I'm just coming up with a number. This is not a political statement or social statement. Which means the probability that the person is not HIV infected, actually infected. Okay? So the probability that the person is not infected is what? 95%. Okay? Comes along company ABC with their super duper, fancy schmancy, high priced HIV test. This company says, hey people, we can correctly detect an HIV-infected person with 99% accuracy. Ooh, ah. That means if a person is actually infected, we will, 99% of the time, actually declare that person as infected. So D means declare as infected. How should I label this probability, by the way? Probability that the test will declare positive, given that the person is actually infected. Are we all here? So we're learning a bunch of things all together. I'm drawing an experiment. We're learning how to label these branches. And ultimately, we want to answer the following question. Given that a test has declared a person as HIV infected, what is the likelihood that that person is actually infected? That's what we're trying to get to. Okay, so the probability that the test comes negative, given that the person is infected, is what? 1%, 0.01. And this test, also, every test has a false alarm probability. Which one of these? So how many points do I have in my sample space? 4. I have 4 possible outcomes. Infected and declared as infected. Infected, not declared as infected. Not infected, declared as infected. And not infected and declared as not infected. I have 4 possible outcomes in my experiment. This thing here is called a miss. Which one's a false alarm? Which entry among these 4? Third one from the top. This is a false alarm. The same scenario holds when you are talking about a context of radar and trying to detect whether there's a plane out there. Either there's a plane out there or there's no plane out there. And the radar will detect and show you a blip on the screen, or it won't. There's one scenario where you have a miss. You have a missed airplane. In the case of war, that could be disastrous. Or you will have a false alarm, in which case you just fire off an anti-aircraft missile and you lose the money that was spent on that missile. Taxpayers pay for it, but at least lives don't get lost. Okay, so we have these contexts all over the place, and the model is the same. Okay, so now the super-duper test, it has only a 10% false alarm rate. So the probability that an uninfected person will be declared as infected is 0.1. And the probability that that person will be correctly excluded from being infected or not correctly declared as uninfected is what? 0.9. Okay. Here's what I want you to figure out. Oops. I want you to figure out the probability that a person is actually infected given that the test says that person is actually infected. Notice this is not the same as, so I want to make sure everybody can read what we're trying to compute. This is the probability that a person is in reality actually HIV infected, given that the test says that person is infected. You want this probability to be low or high? You want it to be high. You want it to be very high. Because otherwise, you declare, the test comes positive, you're going to have to go to, counseling to deal with that trauma. This happened to my sister, not with HIV, but with cancer. She was misdiagnosed with thyroid cancer. And, we went through a very difficult time until it was excluded. So it's not fun being declared as sick when you're not sick. Okay? You can turn this into a DNA test. You can turn it into any kind of context you want. All right, so here's what I want you to do. Bayes' rule says what? We don't have this probability, correct? Do you agree that in the tree diagram, I did not give you this probability? I gave you probability of D given H, but I'm asking you to figure out the probability of H given D. So how would you do it? What's the formula? Reverend Bayes says what? Probability of D given H times probability of H divided by probability of D. Notice the numerator is simply the probability of D intersect H. This is the same as the probability of D intersect H. And the bottom is the probability of D. So, when you look at your sample space, which outcomes correspond to D? How many sample points correspond to D? Test comes positive. Which entries? From the top down. First one? Yes or no? Second one? Third one? All right, so compute the probability of D, please. We don't have a whole lot of time. And I don't want to turn this into a page turner. Let's get to the final answer today. Probability of D is the probability of D and H. How do you figure out the probability of D and H? D and H plus the... What? Oh, no. I brought my my mouse pad, so it saved me. I think I just slipped over my mouse pad. Where was I? Yeah, so the probability of H and D, this is H and D, correct? H and D. And the probability of H complement and D. Again, law of total probability. So this is the probability of D and H plus the probability of D and not H. What's the first term? How do I compute that? In terms of probabilities that you have been given. Can you write this as in terms of the conditionals? How do I get to this top outcome? H and D is equal to probability of what times what? H times probability of D given H. Okay, let's do that. What is the probability of H? Whoops. Probability of H times the probability of D given H. That's this term here. Plus the probability of H complement times what? D given H complement. Can you compute that and give me each term and then give me the sum? Talk to each other. Let's crowdsource this. Let's see how many EECS and LNS students it will take to get the answer. What happened? Oh, sure. There you go. Okay, what's the answer? What's the probability of D? What's the numerical value of the first term? 0. What? 0.495 plus, what's the second term? 0.095. Okay? And the numerator of Bayes' equation is D and H. What's the probability of D and H? Well, we've computed it here. It's just this first term, right? That's probability of D and H. So the probability that the person is actually infected, given that the test declares they're infected, is the probability of D and H over the probability of D. And so the numerator is what? 0.0495 divided by 0.0495 plus 0.095. And what is that final answer? Point what? 3460. I'm sorry, 3426. 25? 256. Let's round that to 4. Is that good? The test declares the person as infected, but the probability that the person is actually infected is only 34%. So much for that super-duper test, huh? This is why there's been so much controversy about these tests. All right, see you Thursday.